All right. So, circular motion. Now, up to this point, we've only considered things going in straight lines. Straight lines.
Chapter 10, all right?
No, these are 9, 10, and 11. I don't differentiate. Now, we will consider motion along a curved path now. Circular motion. Circular motion, just like our little graphic there. Things going around in circles. Like we said, in order to have something going on a circle, you must have a force on it. You said yes. All right, so some terms we need to learn. Terms we need to learn. One is axis. Which is the point or line round which an object rotates, revolves. Okay? Now, although rotate and revolve both describe circular motion, they describe different kinds of circular motion on that. But the axis is at that point, it's the center. It's the center of the circle. That's the axis. Rotation, that would be our record. It's circular motion with the axis inside the object. Inside. So if you look at me right now, watch me, watch me. I am rotating. I am rotating because the axis is right here in the middle of my body. So I am rotating around my axis right now. Rotating. Revolution or revolving. That would be our little bugs. Our little bugs. Now, our little bugs are going around the center. Those are going around. Is the axis inside the bugs? No. Revolution or revolve is circular motion around the axis. Around the axis. In other words, not inside. And this is basically how you define these two. Is the axis inside or outside? So if we look over here, right now, if you guys watch me, I'm going to revolve. So now I am revolving around a center point. Notice there's some place on the floor here around which I'm going. I am revolving around that point. Yes?
The Earth revolves around the sun.
Yes. So the Earth, so the Earth revolves around the sun. It rotates on its axis. So how long does it take the Earth to rotate one time? 24 hours. It takes the Earth 24 hours to rotate one time. I heard a lot of 24, so 24 hours takes to go around one time. How long does it take the Earth to rotate? 365 days. 365 days to rotate around the sun. Notice the axis would be inside the sun. Anyone need more time? All right, so if we look at this, notice we have rotation. There would be our axis here. It's going around in a circle like this. Our axis, we can see the axis, it's going around. It's inside the object. Revolution, this would be like the moon. Notice the axis. Here would be the axis. We're looking down on top, and the moon goes around the Earth, like that. All right, which leads us to timing. Obviously, we need to know some things about it. Now, period is the time for one rotation or revolution. In other words, around the circle. 1 period of time. Our symbol for period is a capital T. But to go around a circle once, any circle, takes 1 period of time. Now it doesn't matter how big that circle is, or how small that circle is, or how fast the thing's going around. It will take 1 period of time to go around once. Once. The period of the Earth's rotation is 24 hours. The period of the Earth's revolution is 365 days. How long it takes to go around one time. Frequency. Now frequency, we use the symbol F. Sometimes you see the Greek letter nu, N-U, nu, looks like a squashed V. We will be using lowercase f. And we measure it in hertz. Notice the capital letter, so it must be named after somebody. A guy named Hertz. Not the guy who does cars. All right? And it's the number of rotations or revolutions in a certain period of time. So whereas the period is like, if you're on the merry-go-round, the period is how long does it take the merry-go-round to go once around. Frequency, but how many times is it going to go around in 1 minute? How many times does it go around in 1 minute? And a hertz is actually 1/seconds. That's what hertz means, something per second. So revolutions per second, rotations per second. You know, RPM, revolutions per minute. That's a frequency. You know, if you have that little tachometer on your car, tells, you know, it's like you rev up your engine, it goes up to like 3,000-4,000 RPM. Instead of telling you your engine crankshaft is going around 4,000 times per minute. That's what it measures. The tachometer measures basically how many times your crankshaft goes around on that. And there's a relationship between them. They are inverses of each other. Period equals 1/frequency. Frequency equals 1/the period. So T equals 1/F. F equals 1/T. So if you know one, you know the other. Okay? You know one, you know the other. But one thing you want to know for period is, remember, that is that one time. You go around the circle once. One time on that. Anyone need more time? Rotational speed or angular velocity. Both of those terms are synonymous. If I say angular velocity or rotational speed, I am talking about the same thing. To be honest, I usually say angular velocity. Okay, just to let you know. Our symbol is the Greek letter omega. This is a lowercase omega. Kind of looks like a squashed W. This is the Greek letter omega. It's lowercase. Uppercase omega looks like a horseshoe. This is the lowercase. And our unit is the radian per second. In other words, and this is how much arc of the circle you cover in a period of time. How much of that circle are you going around? Now, do you need to put your calculators in radians? No. We are not doing trigonometry. If we were doing trigonometry and we were going to do it in radians, we would put our calculator into radian mode. We do not need to do that. We want it, and besides, in physics, we usually always do trigonometry in degrees anyway. The radians measure arc length. Is how much angle. How much angle is there? All right? Anyone need a little bit more time? So, the linear velocity, and this is the velocity we've been talking about, is also called the tangential velocity. Why? Because it is tangent. Tangent. So there would be my velocity vector. So here, right, here's our radius, r. They're at a right angle. I mean, To be a tangent means you touch at one point and you are perpendicular to the radius. Now notice, this is the direction I want to go. So if whatever force, remember we said there has to be a force that causes us to change direction. If that force went away, what's my object going to do? It's going to go in a straight line. And this is the direction anything wants to go that's undergoing circular motion on that. It wants to go off in that straight line. Alright, so this is the tangential velocity, which is different from that angular velocity. Remember, angular velocity is how much of the circle do I cover in a period of time. Anyone need more time?
I didn't just draw that.
Hands are sufficient.
Alright, I got it.
Now, to keep in mind, first of all, how far is it around the circle? How many radians is it around the circle? How many pi? 2 pi. Remember, one circle equals 2 pi radians. Okay, so you have to remember that to go around the circle one time is 2 pi radians. All right? So angular velocity is the same everywhere on the rotating or revolving object. So if we look at these two little guys, ignore what the words say right now. These two little guys. Think of the merry-go-round horse. Now, the merry-go-round horse, if you're on the inner horse or the outer horse, which of you takes longer to go around the circle once? Which one takes longer to go around the circle one time? Neither! Yes, it is the same. It takes the same amount of time for the inner horse to go around one time as the outer horse. Because if it took different amounts of time, would they still be together at the end?
No.
No. In other words, they covered that 2 pi radians in the same amount of time.
Jump.
They covered 2 pi radians in the same amount of time. Which means if I cover the same amount of radians in the same amount of time, I must be going the same angular velocity.
What kind of road?
The angular velocity is the same everywhere on a rotating or revolving object, no matter where you are on this platter. No matter where you are in the merry-go-round, your angular velocity is the same. However, the linear velocity depends on the distance from the axis. Now let's think about this. This little guy follows that path. That little guy follows that path. By the way, what do we call this distance? Circumference, right? This bug has to follow circumference because it's that distance away. This bug follows that circumference because it's that distance away from the center. Are they traveling the same amount of meters around the outside?
Nope.
No. So, since they both take the same amount of time to go around, we already established that, and the outer bug has to travel a longer distance in the same amount of time, what can we say about its linear speed? The one on the outside must be faster. This one outside, and if you've ever been on those little toy merry-go-rounds at the playground, where is it harder to hang on? When you're toward the center or when you're on the outside?
On the outside.
The outside, because you are moving faster. You have a greater inertia on motion of inertia. So they're different. So angular velocity, same everywhere. Linear velocity, farther you're from the axis, the faster you're going. That's like, you guys probably don't have as much experience with this unless you ice skate a lot, but people will get along the line of people skating. You get that outer person. What happens to them? They just kind of get flung off the side, right? On the end. So our formula for angular velocity, omega equals the Greek letter theta. Theta is our arc length. That's how many radians of arc around the circle. Again, there are 2 pi radians in one school. Divided by time. Divided by time. Our conversion, linear velocity equals the angular velocity times r, where r is the radius. In other words, how far are we from the center? The thing is, if we said this, well, we want to know what is the angular velocity to go around a circle one time? Well, if I go around a circle one time, how many radians have I gone through? 2 pi. How long does it take to go around a circle one time? What do we call that? The period. For any rotating or revolving object, its angular velocity is always going to be equal to 2 pi divided by its period, whatever that period happens to be. So you can calculate out an object's angular velocity just by, if you have a stopwatch, because you can time how long it takes to go around once, and you know it has to go 2 pi radians. All right, so that's an important little, it's a corollary of this one. Now this is for any angle in time. This is specifically 2 pi in period. 2 pi in period. Questions? Anybody need more time? Which leads us to angular acceleration. Angular acceleration. Now, angular acceleration, we use the Greek letter alpha. This is a lowercase alpha. Kind of looks like a fish. Kind of looks like a fish. Uppercase alpha actually looks like an egg. This is the rate of change of angular velocity, right? Acceleration is the regular linear acceleration. A, we've studied about before, is the rate of change of linear velocity. This is the rate of change of angular velocities, how much that circle, how much we increase as we speed of the circle. And it's caused by a torque. Remember, torque was one of your vocab words. Remember, torque is to circular motion what force is to linear motion. It's what causes an angular acceleration on that. Our unit is the radian per second squared. Notice in these angular quantities, what is radian replacing?
Radian.
In all these little units, radian replaces meters. Notice it replaces meters. Meters on that. Which means you need to get out that piece of paper. Remember I told you to have that extra piece of paper. You don't want to lose that. But if you keep it in your notebook, just make sure it's just alone. You don't put any other notes on that sheet other than these analogs.
What's the title?
Well, the analogs. I'll put it up next. Anybody need more time on this page? So we have our analogs. And so you want 3 columns. One is linear, one is circular, one is conversion. Now we're going to put our first 3 on today. Like I said, there will be a number of them as we go along. So in linear quantity, first we have distance. We have distance. And usually it's the symbol is D in meters. Our symbol D in meters. In circular quantities, we have arc length. Arc length, theta, in radians. And if I want to convert from one to the other, D equals theta times r, where r is the radius on that. By the way, if we were talking about one circle, theta would be equal to what? 2 pi. 2 pi r is the distance around a circle, which we call circumference. The circumference formula is just the special case of this general formula for one complete circle. Okay? So remember, we're not learning anything new. We are applying what you know before. You already know circumference. That's all this is doing. But if we were only, say, going pi radians, that would be half a circle. We only traveled around half a circle. We only traveled around a quarter of a circle, which would be pi over 2 radians on that. Linear velocity, v in meters per second. V in meters per second. Angular velocity, omega in radians per second. And v equals omega r. And again, r is the radius. R is the radius. Notice, meters, radians. Meters per second, radians per second. Our last quantity that we're going to put on today is going to be linear acceleration. Linear acceleration. I'm just going to ACCEL. A in meters per second squared. Angular acceleration, alpha in radians per second squared, and A equals alpha r. Again, r is the radius of the circle on that. And basically, all the conversions from the linear to the angular quantities are either multiplying or dividing by the radius. Okay, the radius is involved in some way, how far you are from the axis. Remember, r is just telling you the distance from the axis. The axis being the center of the circle. Anyone need more time? All right, so we need to go, so what, we've been talking about these angular quantities, but what makes something go in a circle? There we said already that just from Newton's first law of motion, that in order for this ball to go around a circle, a force must be applied to it. I mean, just from the first law, we know, because if there was no force, this ball wants to go in a straight line. It always wants to go in a straight line. When you are on a carnival ride, you want to go in a straight line. When you are in a car that goes around a corner, you want to go in a straight line. Law of inertia, Newton's first law. Things want to go in a straight line. You must have a force acting upon it to make it go in not a straight line. That force is centripetal force. We use a symbol, F sub c. Anytime we deal with centripetal quantities, we have a little c subscript, c for circle. Our unit, like all other forces, is the Newton. Capital N. This is the inward force that causes circular motion. The word centripetal means center seeking. Center seeking. So notice, and what's causing my ball to go around in a circle?
The string.
Me, right? Me, the string. But I'm pulling on the string, and I'm pulling which direction? Inward, right? I'm pulling inward on the ball to make it go around in a circle. This is toward the center. Anyone need more time? All right, so the force is always toward the axis. And since the force is perpendicular to the tangential velocity. Now, since this force, this centripetal force is perpendicular to the tangential velocity, is it ever going to make the speed change of our velocity? In other words, is it going to make us speed up or slow down? Well, let's consider this. Remember we talked about the sailboats, right? And you have that sail. And the sail, you have that force. And then you have a force that's parallel. Then you have a force that's perpendicular. And our sailboat is moving that direction. The force is perpendicular. Does it make my sailboat go any faster or slower? It doesn't do anything. All it makes is that it makes basically this force that way wants to make my sailboat change direction. That's all centripetal force does. It only changes direction. You might want to write that down. Centripetal force only changes direction. It never changes how fast or slow you are going. Because this little ball, is it going at a constant velocity around my head? Yes, it is. Which means the speed isn't changing. But is its direction always changing? Yes, it is. Direction is always changing, because if I was that little straight vector, right? This is my little vector. As it's going around, it's always changing. Circular motion, you are always accelerating. But the acceleration here is always a change in direction. So this is a case where you are under constant acceleration, but you must always do that. Alright, so centripetal acceleration is that inward acceleration caused by the centripetal force. They're always inward, only changes direction. Only changes direction. So if we look at this little graphic here, this is what direction, no matter what the shape is, what direction you're going. Goes inward. Toward the center, toward the center. And notice as we add more sides to our figure, it's getting more what? More circular. But notice every time it reaches a corner, in order to change direction, the vector, the acceleration vector, is always toward the center. Always, regardless, it's always toward the center. The idea they're showing here that as we keep getting more and more circular, so when we get the circle, it's constantly inward. Constantly inward here.
Wait, one more time.
Now the F word. The F word. There is no such thing as centrifugal force. The F word. There are actually a few F words in physics. This is one of them.
I said the F word.
The centrifugal force does not exist. The word centrifugal means center fleeing. What, in some cases, what you feel, what you think is centrifugal force, this is what is known as a misconception of science. What people think is is either the third law, is the reaction force to the third law, or it is inertia. Remember, you're like when you're going in a car, it feels like, well, when we go around the corner, which way does it feel like you're moving? Outward, right? Guess what? You don't move outward. Your body, what direction does your body want to go? Remember when we were talking about the seatbelt law, right? When you stop the car, does your body want to stop?
No.
It wants to keep going. When you get hit from behind, your body doesn't want to move, the car makes it move. Well, if the car does that in straight line motion, why not the car doing the same thing in curve motion? Remember, when the car turns, what direction does your body want to go?
Straight.
Let's go straight. Let's go straight, right? What makes you go in the circle? The car. Well, when the car pushes inward, it feels like you're going outward. It's not you going outward, it's the car moving inward. Next class, we'll talk about that more in depth on that. And that's inertia, that's how carnival rides work. You know, when you feel the carnival ride, why it feels like you're being pushed outward, it's the ride pushing you inward. You want to go straight. But with this, when I swing this around, you might say, well, Mr. Reese, you know, I feel an outward force. And I would say, yes, you do. And you would say, but doesn't that contradict what you said there's no such thing as centrifugal force? Well, let's think. Where is the outward force? Is it on the ball or on my hand?
The ball's in your hand.
It's on my hand. Remember, third law. I pull inward. But all forces come in what? Pairs. If I pull inward on the ball pulls outward on my hand. Is there any outward force on my hand, on the ball? No. The outward force is on my hand. It's the reaction force. When you feel tugging outward, you're feeling the reaction force. There is no force on the ball because the ball is going to go outward. So, stand right there.
Can I do it?
No.
Please?
No. All right. So, you turn around. Do you trust laws of physics? Sometimes. I'm going to let this ball right here. Now, if I am not correct, and there is such thing as centrifugal force, then I will hit him and he has the right for a lawsuit. But I don't intend to pay any lawsuits today, so I'm going to let it go in front of me. You scared? In what direction did it go? It went that way. It went in the what direction? The T word. Tangential. Tangent. Remember, the velocity vector is always tangent, so when I let go right here, there was no force, right? Once I let go, there's no force. If there's no force, my ball wants to go in a straight line. Newton's first law. It went off in that tangential direction. If I wanted to hit him, I would have to let the ball go over here. You know, it's like the little video of the guy with the slingshot. If you want to use that kind of slingshot, you actually let the rock go when it's over here. You know, they kind of fall through, but they actually let go of it over here. So that's go straight. Pardon?
We should do that. Shoot stuff.
I just did. So let's hear what the author of our book has to say about this.
Except we, not you.
I got this order. I got some water here, gang. I got the water in the bucket. You guys know what I'm doing with this water in the bucket? So we're talking about centrifugal force, aren't we, right? I'm going to take this water in the bucket. What am I going to do? You go right over my head, and when I get to the head top, I'm going to stop, right? No, I ain't going to stop. Not if I can help it. Just go. Okay. Maybe towards you guys, huh? Okay. You have confidence in the laws of physics, huh? But this is water, gang. Okay. How come the water didn't fall out? How many say, well, there's probably no reason for that. It's just that when it's spinning, the laws of physics break down. How come the water didn't fall out? Why? I take the ball and the string, and I swing the ball around and around and around. Or I swing it around like this. Okay? Or like that. How come the ball goes in a circular path? Maybe because something is pulling the ball out. That's what the little kids say. But you guys say, well, wait a minute, there's nothing pulling the ball out. Which way is that ball being pulled, gang? In or out? Begin with an I. Now try it. That's being pulled in. You know why people don't know that? They think that something's pulling the ball out. They think that when I whirl the water around and around and around, that something's pulling the water out. And they have a name for that. You know what they call that? They call it centrifugal force. Center fleeing force. A force going away from the center. But guess what, gang? There is no centrifugal force pulling outward on this ball, and there was no centrifugal force pulling outward on that water. the forces that acted on both these things was pull which way? Inward. I have to pull on that string. If I stop pulling and let go, what's going to happen? The ball going to go out? Or just continue going? And this is the law of inertia.
All right. So, formula. Well, before I get the formula, I'll show you the whole thing.
Hello, I'm Gabriel Musit, and I'm Leon McCall. And our question for our science project is, what is centripetal force? So the hypothesis for our question is that centripetal force is a force that pushes you away from the center when traveling in a circular path. So how are we going to test today? Well, first we're going to do an experiment with these materials. A ball, a string, and a human arm. Human's the best. Okay, so... Oh, wait, I forgot the materials. There. As you can see, we have attached the string to the ball with a human arm. And we will spin it with a human arm around our heads. And we're going to let go at 3 o'clock. And if our hypothesis is right when we let go, it'll go straight away from the circle. Okay, so should I start? Yes, okay. Here we go, everybody. What happened? I let go here, but then it went over there. Do you think our hypothesis is wrong? Maybe we should take again. It can't be. How could it be? We need to understand this further. Let's do more tests. Yeah. Maybe it's possessed. I don't know. We should do it again. Okay. So now I'll do it. Oh. Here we go. Okay. And here we go. I let go over here, but it went over there. I let go here, it went there. I let go here, it went there. I let go over here, but it went over there. It went on an angle. Oh my God. Our hypothesis was wrong. So anyway, if centripetal force was a force that pushed you out, right when I let go of the ball, it would have gone this straight out. But that wasn't the case. When I let go, it went off on an angle. Centripetal force, there must be a force pulling on the ball, and that must be centripetal force, a force that pulls you inward to the center. Great! We figured it out. Let's do some more demonstrations about centripetal force. Yeah. So, we're going to first start off with classic water in a bucket and show how centripetal force affects it. We filled this bucket up with 1/4 of water. Now we're going to see centripetal force in action. Ready, Leon? Yeah? Okay, here we go. Woo-hoo! Whoa! Not a drop fell out. Well, most people think that centripetal force is pushing on the water, keeping it in. But that's not necessarily the case. It's just water is going with the bucket, keeping it in. Oh, okay. Now, we'll see how centripetal force is less powerful than gravity. And that was the demonstration of how centripetal force is less power than gravity. Our next demonstration is the old penny and the balloon trick. Our steps are, you first put the penny in a white balloon, do it under the, and then we start to blow it up. Okay. Guess he doesn't know how to do it. show what centripetal force can really do. Here we go.
Let's go. Can we do that?
That is the power of centripetal force. I hope you learned something about centripetal force today. Ta-ta for now!
Okay. So, our formulas. Now, the thing is, centripetal acceleration, and we're going to watch a little video in a moment. It's going to show us where this comes from. Centripetal acceleration equals the linear velocity squared divided by the radius of the circle. Obviously, the farther you are out, for a certain velocity, the less acceleration it is. It doesn't take as much acceleration to keep you going around the circle the farther you are out on that. But if we take a few things in a case, one, v equals omega r. We already saw that before. Linear velocity equals the angular acceleration times r. This r is the same r as in the formula. And if we substituted omega r in for the v squared, for the v and v squared, we would get this, omega squared r. So centripetal acceleration is also equal to the angular velocity squared times the distance from the center, from the axis of rotation or revolution. You might also recall earlier that we said omega equals 2 pi over the period. There we said that for any circle, anything going around a circle, that the angular velocity is equal to 2 pi divided by the period. So if we substituted in that value in for omega, we get 4 pi squared r over the period squared. Over the period squared. Keep in mind, is pi a number?
Yes.
Yes. Remember, pi is not a symbol. Pi is a number. 3.14159, blah, blah, blah. Okay. Whatever. So a circle is a little low, is about what? 6.2 radians around. Okay, on that. 2.6 radians. And also recall that period is equal to 1 over the frequency. So I also get 4 pi squared r times the frequency squared. So I have 4 ways in which to write down my centripetal acceleration depending on what information. But there is one piece of information I must have. What is the one thing that appears in every single one of these? R. I need to know the radius of the circle. I must know the radius of the circle. Now, centripetal force, like any other force, is just mass times the centripetal acceleration. Mass times acceleration. So all I have to do to any one of those other values is multiply it by the mass. By the mass. So I get mv squared over r.
Wait, so for centripetal acceleration, what's the final equation?
Centripetal acceleration. All of those. We're going to talk where this one comes from. I have a video that shows where this one comes from. All the rest of these are derived from this formula.
So we use it.
Well, we might use all of them. It depends what, I mean, if you were given the velocity, you would use this one. If you were given angular velocity,
Oh, okay, good.
if you were given the period, if you were given the frequency, it depends on what information you might have. Velocity is hard to measure because you didn't know what's the circumference, blah, 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 blah. Omega, this can be tough too, but it's also 2 once around, you time it, you can get that. But basically, 4 pi squared t squared over t squared, that's the thing. The one thing you need is that. Otherwise, we just multiply them all by mass. So we get m times 4 pi squared r over t squared, m 4 pi squared r f squared. So those are all the ways to write down the centripetal force. Just take the mass times whatever formula you're using for centripetal acceleration. It's Newton's second law. And we need more time. Now, this video Very old. Just keep in mind, this is what I was talking about. But this is kind of the way all videos were when I was in high school, unfortunately. So it might make you think, be thankful for Eureka. But the information in this, even though it's very old school, the information they give it is one of the best explanations. Why is centripetal acceleration equal to v squared over r? Where does this formula come from? It's not very obvious where it comes from. Well, we do know we have a linear velocity go around, but why is it v squared over r is centripetal acceleration? All right? Any more time? You might want to. I think the thing says 1951, 1961.
Pretty new.
Guys, it's.
When equal distances, delta s, along the circumference of a circle, are traversed in equal time intervals, the motion is called uniform circular motion. The linear speed, v, is equal to delta s divided by the corresponding time interval delta t, and is constant. The linear velocity, however, is not constant. As the motion proceeds, the velocity vector changes its direction continually, being always tangent to the circle, or what amounts to the same thing, perpendicular to the radius. Because of the changing direction of the velocity vector, uniform circular motion is accelerated motion. In a small time interval, the vector v1 changes to v2. The difference between v2 and v1 is the vector which must be added to v1 to get v2. Another way of finding the vector representing the change of velocity is to add to v2 the negative of v1. The sum of these vectors is v2 minus v1. The change of velocity during any time interval is the vector v2 minus v1, or delta v, and is seen to point inward somewhere near the center. When the 2 points are closer together, delta v points toward a place nearer the center. When the 2 points are extremely close together, delta v always points toward the center. And therefore, the fraction obtained by dividing the vector delta v by the scalar time interval delta t is a vector pointing toward the center. The limiting value of this ratio, as both delta v and delta t approach 0, is by definition the acceleration vector a. Since vector a points toward the center, it is called the centripetal acceleration. The velocity vector and the acceleration vector are always perpendicular to each other, v being directed along the tangent and a along the radius. Having found the direction of the centripetal acceleration, let us now proceed to calculate its magnitude. We again choose any 2 points on the circle. The angle delta theta between the radii is the same as the angle between the velocity vectors. This follows from simple geometry. The magnitude of the vector delta v is small delta v, and the magnitude of both vectors v1 and v2 is small v. If points 1 and 2 are extremely close together, the vector triangle and the space triangle are similar triangles. Corresponding sides are therefore proportional, or small delta v is to small v as delta s is to r. Therefore, small delta V equals small v over r times delta S. Dividing both sides of this equation by delta t, the time interval that it takes the body to go from point 1 to point 2, we get small delta v over delta t equals small v over r times delta S over delta t. As points 1 and 2 are taken nearer and nearer together, small delta v over delta t approaches the magnitude of the acceleration a. Delta S over delta t approaches small v. Therefore, a equals v squared over r. If a mass m has an acceleration a of magnitude v squared over r and is directed toward the center of a circle, then, since we believe that Newton's second law applies to this kind of acceleration as well as to all others, we say that F equals ma, or F equals mv squared over r, and is directed toward the center. This force acting on the body, necessary to keep the body moving in a circle, is called the centripetal force. Motion in the circle does not create, produce, or manufacture this force. It needs this force, and some outside agent must provide this force. It may be provided in a variety of ways. For example, by gravitational attraction, or by means of a string. If the string is broken, the centripetal force ceases to act, and the body continues to move in a straight line in the direction it has at the moment the force stops. Since the direction of motion is along the tangent, the body continues along the tangent. Another example is provided by the rails of a loop-the-loop. Or by a magnetic field acting on an electrically charged particle. If the magnetic field is uniform, and the particle starts to move perpendicular to the field, it continues to move in a circle. This is the starting point in the operation of a cyclotron, one of the many varieties of atom smashers that play such an important role in modern nuclear physics.
You can make videos of this in the
All right.